Hello guys, so welcome back to our lecture 4. We're gonna continue our journey with the equilibrium condition of the p-n junction. So last time we learned that if we put together, in contact an n-type sample and a p-type of sample, holes and electrons from both sides will start to diffuse to the other part. This will create a diffusion current, and by the time there will be electric fields that will be created at the junction, at the contact, because as we said, each hole leaves the p-type to the n-type will leave behind a negative ion, and each electron that leaves the n-type to the p-type will leave behind a positive ion. So we will end up at the equilibrium with equal drift current and equal diffusion current that will cancel each other. Okay. At that time, which should be at infinity. Okay. This is called the equilibrium. Okay. Because you have two quantities that equalize each other. Okay. At that time, if we look at the, our material now, our, with the contact in between, we'll find that our material is divided into, we can say 3 regions, not 4 regions. Okay. N-type region, like this one. So let's like N-type region, B-type region, and around the contact, a new region called the depletion region has been, created. Remember, the electric field that is generated due to these ions will prevent the motion of carriers from B to N and from N to B. So that region that has only ions does not contain any carrier, any current carrier. I mean, doesn't contain holes or doesn't contain electrons. That's why they call it depletion region. It's depleted from any current carrier. Okay. And once we have an electric field, once we have positive electrode, negative electrode, we also have a potential. It's naturally created potential, just like the electric field. So this potential will have this direction here from the negative to the positive, and we call it V naught or VBI, barrier potential. So at equilibrium, a contact potential between brackets barrier potential is created in the depletion region. So if we call this, for example, if this is, the x-axis, if we call this x1 and this is x2, so basically V naught, which is VBI, the people call it with many symbols. Some call it V naught, some call it barrier potential, so they call it VBI. Okay. All these names are, just valid. We're gonna go with 2. So you will find me sometimes call it V naught, sometimes call it VBI. Okay. So this is basically the voltage between the 2 points x1, x2, or Vx1 minus Vx2. Because we know that always the positive terminal has bigger voltage than, or larger voltage than the negative terminal. Okay. Good. Now the question, can we determine this naturally created potential VBI or V naught or the contact potential? And the answer is yes, we can measure it. Okay, and we have a fact here that we discussed the last time and also at the beginning of this part or video, is that at equilibrium the diffusion current will be equal to the drift current. So let's see what's gonna happen if we equate them to each other. So at equilibrium, Jn will be equal to Jn drift will be equal to Jn diffusion, and Jb drift will be equal to Jb diffusion. You can go with any of them. Both will lead to the same conclusion about VBI. I mean, now we're gonna, calculate an expression or find an expression for VBI or V naught. And both can lead you to the answer, to the correct answer. So let's go, for example, with JB. Okay, so JB drift equal to Q mu B B E, and JB diffusion is equal to Q dB of x by dx. There is minus here, yes. Minus Q dB of x by dx. And why the minus? Because we said that, you have dB by dx is already should be minus, so this minus will cancel this minus. So let's equate these to each other. So Q mu B B E equal to minus Q dB of x by dx. We're gonna multiply by dx both sides, and at the same time divide by b. So we're gonna multiply both sides by d of x, or sorry, dx, and divide by db, both sides. So this will be equal to, let's have this first, so minus q dB of x over b equal to, of course q will go with q, so we don't need to write it again or to include it, equal to mu b e dx. Okay, that's good. Now we can take the integral for both sides, so we can integrate this and we can integrate this like this. So why we kept dB and mu b outside of the integral? Because they are constants. So dB, remember dB and mu b are constants. Why you didn't consider E as constant? No, E is not constant. E actually is unknown till this moment for us. We are not interested in calculating E, but we can. It's easy. But I am not interested in it. Okay? And if we calculate it, you will find that is E is not uniform, is not constant. That's it depends on the distance x. So we cannot move it out of the integral. We need also, limits for our integral. Okay, remember this V naught is restricted by the depletion region. It's 0 outside the depletion region, and also E, the electric field, is 0 outside the depletion region. It's only between the electrodes, between the the positive electrodes, this ion that we can imagine as electrode, positive electrode, and this negative ion that can imagine as also negative electrode. Okay, so let's take the integral from x2 to x1. from the negative to positive, I mean, from x2 here to x1. So there should be limits also to the second integral. And what is in the second integral? It's b of x. So what is b of x at x2? Remember, x2 is is at the it's located in the B type region. So at x2, the density of the holes are PP. And what is the density of holes at x1? The other limit of the integral. Remember, at x1 is belong to the N type region. So it's a minority there, which is Bn. Good. Remember, Bn is less than Bb. Because this is, here it's a minority, here it's majority. So in a practical case, PP is larger than Bn. Okay, but BB is in the lower limit. To change the limits, we can use this minus here to change the limit. So this can be so we can remove the minus, but it changes the limits from Bn to PP. So this will be dB Pn to PP, dB of x over P equal to. Let's now consider the second one. Okay, if you guys studied, electric field theory, we have a fact there that the voltage, the potential, is equal to minus the integral from the positive to the negative from x1 to x2. From the positive electrode, so x1, to the negative electrode, so x2. E dx. Remember, we don't know E. If we know it, we just, make the integral, but we don't know it. But we know the integral has a whole, has a relation to V naught. In our case here, this is actually V naught or the VBI. But unfortunately, we have here x2 to x1. Okay, not x1 to x2 like this, right? So from this relation here, V naught, again, you have a minus. This minus can flip the limits of the integral. So it can be, we can remove the minus and make the integral from x2 to x1. x2 to x1 e dx. What is this? This is basically this one. So this is equal to mu p V naught. Or VBI, name it whatever. Okay. And what is this? This is a very easy integral. This should be ln p from Pn to Pp. Remember, we are interested in calculating V naught. So let's divide both sides with mu p. So V naught equal to dB over mu p. And this ln is actually ln Pp minus ln Pn equal to dP over mu p ln Pp over Bn. Very nice. Very nice. Remember, guys, the last fact or the last, information that we discussed in lecture 3, which was Einstein relation. From Einstein relation, we knew that dB over mu b, or d over b in general, over mu, I'm sorry, equal to kt over q. Any d over its corresponding mu, dB over mu b, or dn over mu n, equal to kt over q. Okay, so V naught equal to KT over Q ln PP over BN. We said also usually PP at room temperature, we have several facts here at room temperature. Number one, PP equal to NA and N equal to ND. And NN PN equal to NI square. So PN is equal to NN. Equal to NI square over NN. So PN equal to NI square over ND. Put a square around this and put a square around this. So this is the first fact. Second fact at room temperature is that we know KT. We know KT over Q. Room temperature is 300 degree Kelvin. So if we substitute in here, we know Q, 1.6 10 to the power minus 19. We know K, Boltzmann constant. So this is basically equal to 0.026, electron volt. They call it basically thermal voltage. This is called thermal voltage. And they just say it's a 26 millivolt or 0.026 volt. Okay, so basically V naught or VBI equal to at room temperature, and usually we work at room temperature, 0.026 ln. Let's now compensate for PP and PN. PP is NA. PN is NI square over ND. So ND will go to the numerator. So NI square in the denominator, and in the numerator we have ND. And that's the lovely equation or expression for V naught. As you see here, it doesn't depend on, it looks like it doesn't depend on something in the B. Although we started from something in the B-type material or B-type side, we end up with something general, that gather both sides. Na from the B side and Nd from the N side. And Ni square is constant for the material. Okay, that's very nice equation. Very nice equation. One last observation here, usually the doping it is between 10 to the power of 15 to 10 to the power of 17. 10 to the power of 15 to 10 to the power of 17. And for silicon, Ni is equal to 10 to the power of 10. So we even know, or we can estimate NA/ND over Ni square. And from these facts that we know that we can estimate Na and ND, practically it's between 10 to the power of 15 to 10 to the power of 17. And the Ni is 10 to the power of 10 for the silicon. V naught or VBI is between 600 millivolt to 800 millivolt. On average, 700 millivolt or 0.7 volt, as many people, use. And we're gonna use 700 millivolt because it's average value between 600 and 800 in our course a lot. Okay, guys. So this is, a very basic property of the equilibrium condition. This is naturally created voltage, the built-in voltage or the contact potential or the barrier potential, is one of the fundamental, characteristics of the equilibrium condition. And actually, we're gonna relate to it when we do other conditions for the being junction, like for example, forward condition or reverse condition. I'm gonna use this VBI, because it's gonna increase or decrease. This property, VBI, it's gonna increase or decrease based on the condition. Okay, so thank you very much for watching this video and see you in next videos. Bye-bye.